Hey everyone, and welcome to the Weekly Space Hangout for Friday, October 2nd, 2015. I'm Fraser Cain, publisher of Universe Today, and today we are going to talk about water on Mars, obviously, India's first space station, first space observatory, new pictures of Sharon, a whole bunch of exoplanet news, map of Ceres, the new Discovery missions that were announced, and the search for missing gravitational waves. Now, we don't have a special guest today, but
You have
we
me.
do have our special guest once again is Sandy. No, but we have a new panelist who's going to be joining us this week and perhaps weeks in the future. So, first week turn makes you our special guest, Kimberly. So why don't we'll start with all the other panelists, and then we will introduce you. So first, we're going to start with Sandy. Hey, Sandy.
Hi, how are you doing?
Good. Just Sandy today, though.
Yeah.
We got Dr. Brian Coberland. Hey, Brian.
Hi, nice to be back again.
Yay, Brian's back. We got Morgan Renberg. Hey, Morgan.
Hey, Fraser.
And we've got my Astronomy Cast co-host, Dr. Pamela Gay. Hey, Pamela.
Hello, everyone. I am also here not representing NASA. I think it's safe to say any of us who have NASA funding are not representing NASA.
Which I think we can say you have NASA funding.
I do. Well, we don't know how much yet. I mean, I have an award letter and have a press release. But, our CosmoQuest team was one of the 27 teams selected to be a NASA education partner, and we are going to be continuing CosmoQuest and growing it out to do more and more citizen science projects with more and more missions and hopefully more and more of you out in the audience.
Absolutely.
I've got my CosmoQuest shirt on.
Right on. Yeah, no, I mean, the Weekly Space Hangout, this thing you're watching right now started as part of CosmoQuest, and,
and it still is. It's just running on your channel.
Yeah, exactly. But we are all CosmoQuest, and this is absolutely fantastic news. I know it was an enormous, stressful, crazy time leading up to this funding announcement, and it couldn't have happened to a better group of people.
And this means that this year's Hangout-a-thon is 36 straight hours of science only, baby.
Not asking for money.
No more asking for money. Science only.
That sounds great. Right, and so joining us for the first time, and hopefully not the last, is Kimberly Cartier. Kimberly, welcome to the Weekly Space Hangout.
Thank you. It's so great to be here.
So for people who have perhaps no idea who you are, they haven't seen the multiple Nobel Prizes, can you let everyone know who you are?
Well, I'm running out of room for my Nobel Prizes on my bookshelf. Every
As you do.
You know how that works. Yeah.
Yep.
I'm a graduate student at Penn State University. I study extrasolar planets and all of their myriad of forms and shapes and temperatures that they come in. Hot Jupiters and rocky planets and planets that are so hot that they start shedding all of their material all over the place, and we get really confused. But it's been a great few years in exoplanets for sure, and there's great stuff to come, so I'm really glad to be here to share this with whoever happens to be watching.
Isn't it fantastic that we have an extrasolar planet beat now, that we have enough discoveries happening in exoplanets and enough weird, different, and interesting kinds of planets being discovered that it makes sense to have a person who mostly focuses on exoplanets? What a time.
It's such a fantastic thing.
I saw this fabulous sign the other day. I want to say it was one that Sarah Seeger put up that said, every exoplanet is unique, all 10 billion of them. And this has got to make being an exoplanet scientist so much more exciting.
Yeah.
It really does, because in any direction that you look, you're guaranteed to be looking at a star that has a planet. And you have no idea what that planet is, and it's probably completely different than anything we've seen before.
And so, what kinds of planets are you mostly focused on?
Well, I have a particular love for rocky, habitable zone planets, as many exoplanet scientists do, and that's where I actually started my research, looking at rocky planets around in binary systems, actually. So 2 stars, lots of planets. And then I moved into those disintegrating planets that I mentioned. There are a few really strange signals that Kepler picked up that turn out to most likely be planets that are so close to their star receiving so much heat that they're actually shedding material like a comet would.
Wow. That would
Uh,
not be a good place to live.
Hey,
Not very-
Mercury does that.
Mm-hmm.
Mercury sheds hundreds of tons of material every day.
Because it's getting blasted by the sun. That's its
these-
atmosphere,
yeah.
right? It's rock atmosphere.
Mm-hmm.
Yeah, these are even more extreme than that. So you have so much material, you actually get a whole sort of like one of the rings of Saturn, just like a cometary debris ring around the star itself. That's really the only way we can see these, because once you shed so much material, you're way too small to be detected by Kepler. So it was a really strange thing that, we looked through the Kepler data and there it was, and we had no idea what to do with it for a while. Now
And
we're
so-
finding more and more of them.
And so do we find these worlds like around newly forming stars or older stars? Is just
No, this is a normal main sequence star. It's been doing its thing for billions of years, and the planet just, had a bad luck of the draw.
and so it's entirely possible that our sun has gobbled up planets like that in the ancient past.
It could be. That's one of the outstanding questions of planet formation is how many planets did we start with? How many did we kick out of there when things were all moving around? And how many of those just crashed into the sun? We have no idea.
All right, well, we've got a bunch of planet stories that we're going to talk about today, so why don't we get to the news? And normally we don't have a lot of time to talk about the news, but this week we've got a lot of panels, we've got a lot of news, and so I think we can get right at it. Now, I want to remind everybody that this is a live, interactive show. You can talk to us, ask us some questions, and the way you do that is use the Q&A app. So wherever you're watching this video, there should be a link inside of it that says that we're interacting with the audience, taking questions live, and if you click that, you'll still be able to watch the video, but now you'll be able to ask any questions that you might want to have. So I'm going to say hi to Ronald Minch and Nat Woods and Richard Strazel and Douglas Crandall and Ignatiy Romanov-Cherengovsky, Bert Walters, Tom Nathie, Giselle Sabarin, Guido Bibra, Tony Lynch, Michael Jobin, Tom Nathie. If I haven't, there's a second time, Tom. Lars Peter Hammer, and Guido Bibra, and Susan Hunter. So, hey, everybody, thanks for joining us today. A lot of these are the members of the Weekly Space Hangout crew, which is sort of really the producers of this show. So if you're looking for a really great space community to join and help make the Weekly Space Hangout, go to the Weekly Space Hangout crew. You can find them on the internet, find it on Google, you can find them on Google+. They're all over the place. I think they even have a Twitter feed now. Anyway. All right, let's get cracking. So I guess the big, you know what, before we get to the big news, who saw the eclipse this week? Morgan.
I did.
Right on. And was it as boring and lame as you thought it was going to be?
It was an eclipse.
I was Killington. Yeah,
Come on, Fraser. It's not lame. It's not limping.
we went down to the beach to see the eclipse, and it was just a total zoo. It was a gong show to try and get down there. There was hundreds of cars down there. The entire beach was packed. There was no parking, and everybody was there to watch the eclipse. I had all faith in humanity was restored, just like that.
I will say, when I went outside and walked down to my neighborhood park to get a good view of it, all down the street there were people out of their houses sitting on their front steps looking at it, and that was really great.
That's awesome. Mm. I'm getting some echo from someone.
It's probably me. Hold on, let me mute myself.
All right, we'll see what happens. Yeah, so I hope you guys enjoyed it. Nope, it's not you. I'm guessing it's Kimberly. Do you have headphones? Yeah, do you have headphones, Kimberly?
Yes. Give me 1 second.
Just mute yourself and then put in some headphones.
Yep.
That would be great. Thank you. Okay, great. Well, let's get on with the. So anyway, if you didn't get a chance to see it, I'm sorry. You will have to wait a couple of years. And for I guess for the people who are on the other side of the Earth, sorry, but you got some other ones. We're at the fourth one. The other big thing is, of course, The Martian is happening tonight. And if you haven't read the book,
Too late.
Still
too
time.
late. Go see the movie. I haven't seen it yet, but I've enough people that I like are really ecstatic about it, and so I think it opens tonight for most places. So that's where we're going in just a couple of hours. I cannot wait to go see The Martian. All right, and let us know if you're going to see The Martian. Okay, water on Mars. Morgan, it turns out there's water on Mars.
Yes, that's right. This week, for the maybe 100th time, NASA announced that they have found water on the surface of Mars. And of course, this is not, in the grand scheme of things, a terribly new discovery. We've now known for a long time that there's water in clouds above Mars, there's water in the ice at the poles of Mars, there's water underneath the surface in the soil of Mars, and there's myriad evidence that water once flowed freely across large parts of the Martian surface. But what we didn't know is that water actually flows on the surface of Mars today, at least in some places, under certain conditions, at some times. And this discovery stemmed from detections made by the Mars Reconnaissance Orbiter, which is one of our fleet now of satellites studying Mars. And what they were investigating were these things called recurring lineae. And there were these strange dark lines that would appear and disappear and seem to shift around from season to season on the surface of Mars. And so they pointed their spectrometer at these locations to measure the chemical composition of the soil here. And what they found was that the chemicals could basically only exist in the presence of actively flowing water. And these were a class of salts we call perchlorates. And what perchlorates allows water to do basically, is it lowers its freezing temperature, kind of like antifreeze, so much that even when it's very cold at Mars, the water can still flow. Now, we're not talking about like streams or rivers or even maybe like running droplets of water, because the pressure is still extremely low at the surface of Mars, but more like sort of wetness spreading out through the sort of sandy regolith or surface of Mars. And so because we see these all over Mars at different times and different places, we don't have sort of a singular mechanism to explain why they happen, but it does seem to be very solid evidence that there is water moving around on the surface of Mars today.
But it seems to happen in the springtime in those regions on Mars, right? That the temperatures are getting to they're getting warm enough that this water can come out of the sides of the craters and flow down the hill, right? Absolutely.
It totally matches what you would expect from sort of a freeze-thaw cycle like we have here on Earth, where during it's cold in the winter and the fall months, the water is locked up in ice, and then as temperature warms, and at certain places on Mars, it can actually be above freezing, above 0 centigrade, on the surface of Mars during the summer, and the water then can begin to flow.
And as you said, by flow you mean seep, and by water you mean poisonous perchlorate.
Right. This is the worst water for life that you could
antifreeze.
possibly imagine.
Yeah.
And so it doesn't really open up a lot of probability for existing life, but it does, I would say, sort of crack that window. Because as we've talked about sort of numerous times in the past on the show, it's much more difficult to create life than it is to sustain it. And so life could have arisen in better conditions in the distant past and sort of clung to existence under these much more harsh conditions today. But given how little water there seems to be and how infrequently it flows and how poisonous this water would be, at least to life as we know it here on Earth, I wouldn't say that this is a place that you'd expect to be teeming with Martian bacteria.
Now, you mentioned sort of before the show that Curiosity is not allowed to visit this water, and it actually is pretty close to where Curiosity is operating, right?
Yeah, that was initially really exciting because one of these patches where this water has been found is less than 50 kilometers from the present location of Curiosity, and at sort of top speed, which is 200 meters per day, it would take about a year for Curiosity to drive its way over and check out this water. But actually, under international law, Curiosity is forbidden from approaching this region because we're always concerned about contaminating other worlds with our own dirty Earth bacteria. And we have different levels of cleanliness. And so if you're going to a place that's really dry and radiation baked, like we thought the surface of Mars was, there's one level of cleanliness that you must basically protect your spacecraft to. But if you think that there's liquid water where you're going, it actually raises that bar much higher, and you have to have a much, much smaller possibility of contamination in order to approach it. And because Curiosity was developed and sent in a time where we thought that the surface of Mars today was likely to always be dry, they didn't undergo these stricter procedures, which would have taken more time, cost more money, etc. And so we tantalizingly have a spacecraft that's almost ideally suited to go and look at these samples, that we just can't send it over there because it would be a tragedy to have an accidental contamination of an Earth microbe that would then sort of forever cast into doubt any future discoveries that we might make.
Yeah, every time I see European starlings and there's rats, in the backyard, that is your invasive species. Imagine if we wiped out the life on Mars with our hardy Earth bacteria. But the more complicated one to think about is what's going to happen if they do send some kind of sample return mission to Mars and it's actually searching for evidence of life. To be able to bring those samples back to Earth, there's a whole other level of protection on top of that. I think it's the level 5 of this 5-part protection, and they pretty much have to sterilize samples before they can bring them back through the atmosphere, because perhaps even more disastrous would be if we brought alien bacteria from Mars to Earth and let it loose on our planet. So it would be like War of the Worlds. Anyway, so that's still there's water on Mars again. Still, not good for growing potatoes. But
I made the comment this week on Twitter that I think the real story here is not water on Mars. The real story here is that you don't really learn that much about a planet by studying just a few kilometers here and there. There's as much surface area on Mars as there is on all the continents of the Earth combined. Imagine landing a car on somewhere on Earth that could drive a kilometer, and that's all you ever knew about the world. You'd either think that the Earth is a jungle or a desert or full of canyons. You would know very, very little about the actual nature of our planet. And what we've discovered here is that Mars is the same way, that we've studied such a vanishingly small piece of it that we're only really grasping at straws to understand the whole of the geology, the whole of any possible biology that could exist on another world.
Awesome.
And you left out one of the coolest human aspects of this story. The 2 researchers who announced this result are grad students, and one of them started doing this research while he was an undergraduate. So this is work that he's been working on for 5 continuous years, 2 separate universities, slowly but surely. And it's not the gray-haired old men who found the water. It was an undergrad with determination who kept at it through graduate school and is now in Nantes, France, giving these results.
There's no magic formula to doing science. You just keep going.
Determination is the magic formula, with some luck mixed in.
A willingness to look at boring information for long periods of time.
Yes.
It's like everything. Okay, Sandy, let's talk about some the newly announced Discovery missions from NASA.
Boat. Sorry.
Oh, sorry. Were you making fun of my accent?
You can make fun of mine any day.
All right.
So every couple years, and not as frequently as we'd like, NASA has a call for their Discovery mission proposals. And Discovery is NASA's small, and I quote small because it's about $500 million for a scientific planetary science mission that's PI-led, which means it's led by one principal investigator rather than NASA saying, you people, you're going to go do this. And so you can't really choose where you're going or what you're doing, but you can propose instruments. So a PI-led mission means that there's one individual who proposes a mission and they bring along other colleagues who can support the mission. And so they support not only they propose a spacecraft, but they propose a bunch of instruments to go on it. So the latest Discovery call, it was due in February, and some people have been working for years on some of these mission concepts. There were about 38 Discovery proposals altogether that were submitted in February. I heard one of them was a joke. Not really sure what that means. So over the summer, review panels met and they evaluated the science and the risk and the possible scientific return from these missions. And on Wednesday, we heard what the down select was. And so they went from 38 missions to saying there will be 5 missions that will be selected for a year of funding to further develop their scientific ideas. And those 5 missions were actually really interesting. And there's 2 of them were Venus missions, one that would collect 63 minutes of data as it descends to the Venus atmosphere. There's another Venus mission, and I think that's very interesting that there are 2 Venus missions because we haven't sent a space probe to Venus in about 30, 35 years. Venus has really fallen out of fashion in the recent decades. Though recently there's sort of been a resurgence of interest in Venus science as people have been putting out more papers in anticipation of a discovery call to make Venus more in vogue. The other three missions are asteroid related. One is NEOCAM, which is proposed by the Jet Propulsion Lab, and that continues on what they've learned from NEOWISE, which was an infrared spacecraft launched to study anything that could be visible in the infrared. And so this NEOWISE would be a dedicated spacecraft to find asteroids before they find us, find things about the size of Chelyabinsk that could really ruin cities. Another mission is called Psyche. It's going to visit the metal world, Psyche. There's a lot of metal today. One of the grad students who was working on these recurring slope lineae on Mars, he's actually a metalhead. He was in a metal band before he was a student. Rock on, man. So one of them is to visit this asteroid Psyche, which we think is this metallic core of a asteroid where the mantle and crust have been completely blown off, and all that's left is this metallic pit, maybe covered with olivine and some other minerals. And the final mission is would go to Trojan asteroids of Jupiter. If you're a Lagrange L4 or L5 society member. These are Lagrange points, or stable points in space ahead of Jupiter and behind Jupiter. I just did the math for that last week in class. It's lots of fun if you like trigonometry. So it would visit Trojan asteroids in front of Jupiter and behind Jupiter, which is really exciting because we've never had a mission to a Trojan asteroid. There's a couple of things that are interesting here, is that first of all, there's 2 Venus missions, which is kind of unprecedented, and the rest of the other 3 missions are asteroid missions. So asteroids are in, and Venus is in. And there's also no missions to the outer planets. This discovery call does not allow you to use plutonium to power your spacecraft because there wouldn't necessarily be enough ready by the time that there's launch. So in order to go to the outer solar system, you'd need solar panels the size of a tennis field with a little spacecraft on it with 1 or 2 instruments. So while there are missions proposed to go to Io to study volcanoes or to go to Saturn to study plumes on Enceladus, those aren't selected in this time around. So that's really kind of bad news for the outer solar system. This is bad news for people who study Io. This is bad news for people who study Enceladus. It's bad news for people who study rings like Morgan. Hi, Morgan. So it's sort of interesting that the outer solar system is going to sort of go dark in the near future for researchers for whom that's what they've spent their career studying. So the other thing that's interesting beyond the scientific sides of this is that of the 5 missions selected for further development, 4 of those have women who are the principal investigators. And I think a couple of people are looking into previous discovery calls to see what sort of the gender balance of who the PIs were in the past, but I think this is the first time you've had 4 women as the PIs for missions, and I think I've met 3 out of the 4 of them, and I can assure you they're all great, and the deputy PI on the Trojan mission is a woman as well. So I think it says some good things about sort of progressiveness in planetary science when it comes to space exploration. So hopefully things continue to progress in a good way, but I think also it means that you've got a lot of focus on the inner solar system, and poor Venus, which has been neglected, is sort of getting its time in the spotlight again.
So what are the, like, how many of them in the end will they be able to have budget to afford? Is it just going to end up being 1?
It's just going to be 1.
It could be 2.
It could be 2.
Or 2.
Or 2, depending on sort of how much each mission proposed costs. And I think a lot of these missions that were proposed could have flown and could be selected and could produce excellent science, but there's just not enough NASA funding to do this. And the cadence of discovery calls and discovery proposals being funded is not high enough as we'd like. The next discovery mission that's launching is InSight, which launches in March, and Morgan and I are totally going to road trip out there to go see it. When was the last discovery call before InSight? What was the last mission before that one? Is that Dawn? No.
Kepler?
Anyway, what? Morgan?
Long ago, and the problem with how long ago these were, and I'm sure that someone can Google all of this for us. You have people who will spend 5 or 10 years of their career developing these plans to go forward for these discovery calls that are so rare, and you put all your time and effort. At a certain point, you actually hurt your career because you're not publishing as much science because you're so focused on writing the spacecraft proposal. And when you're not selected, it hits you in three different ways. It hits you in the heart because the science you dreamed of doing you don't get to do. It hits you in the wallet because a lot of people working in planetary science are funded through the spacecrafts that they work for. So this can be a career ender. And then third, it hits you in the you've spent all of this time dedicated to this one area, and now you have to go back and catch up and play the catch-up game to go figure out, well, where is the hot science nowadays? And the poor Mars people have gotten yo-yoed over the years because a few years ago we all listened as we were told, those of you studying Mars need to find another planet, and we got angry at the Lunar and Planetary Science Conference because we thought all the funding was going away after Curiosity. People redirected their efforts. We were all told outer solar system, outer solar system. Now nothing's going to the outer solar system, and yes, Trojan asteroids are a border object, but and Mars is what's hot, and Venus is what's hotter.
Yeah, I mean, I'm always really excited with these smaller discovery missions because they'll go to like a new place and answer some really interesting new questions a lot of the time. I mean, New Horizons was one, right? And that paid off. But then at the same time, you've got to look at things like the Hubble Space Telescope, which are these really big, much more expensive, complicated missions with lots of instruments. And you look at the amount of science that's coming out of those as well. Or you look at, say, Cassini, right, which has just been delivering the goods year after year after year. So I'm sure the battles between various interest groups in this can get pretty heated, right? About should we focus more on these big missions are going to go way over budget, they're going to gobble up all the money like James Webb, but at the same time will produce science that will be usable for years and years and years. So it's a I don't even want to have the argument. Definitely don't want to have the argument here.
It's why we have the decadal survey. The decadal survey is where all of us argue.
Yeah,
it works.
Perfect.
As of the last budget, I will just say that NASA's intention is to increase the frequency of small Discovery class missions and reduce the frequency of medium-sized missions like New Horizons. And so we could see more of these smaller missions that get us to more places, but naturally they come at a cost of being less capable than and less ambitious than a mission like OSIRIS-REx or New Horizons.
I've got a question from Chris Macca. Does NASA take public perception, aka the cool factor, into any of the Discover mission selections? Sandy, does NASA care if the public thinks it'll be cool?
I think the review panels, I don't even know what criteria the review panels evaluate on, but I think it has to do with scientific return, risk, cost, and a couple other things. So
they do have communications plans that they have to put into the proposal, and you can, in general, look up what does either the request for proposals or the cooperative agreement notice, depending on the type of the mission. They list the specific criteria, and communications is one of the things that if you can't communicate it coherently to the public, that's part of the Space Act agreement. We have to be able to do that. So it's not so much what's cool as what can be communicated how.
Well, and I think there's also a difference between what's a stated official point of selection and maybe what's in the hearts and minds of people as they're making these decisions, because you can imagine the difficulty in weighing the possibility of a 10-year mission like we got with Opportunity versus 53 minutes to float down to the surface of Venus. And while those may have equal scientific value, it could easily be perceived as much more bang for your buck to do something that's longer lived just because of that. And that, I think, maybe historically has played into some of the difficulties that Venus in particular has had in getting selected, is that unless you're going to do a Venus orbiter, you're talking about hours or at most days, much like New Horizons, as opposed to something like a Mars lander or rover or something to the moon.
What about some kind of steampunk Venus balloon? All right.
Yeah.
Let's
Yes.
Was that one of your trigger words? Steampunk, Pamela? Okay,
Yes.
let's move on. Kimberly, you ready?
Yeah.
I gotta leave, Fraser, so I wanted to thank
Well-
you all for a wonderful weekly space hangout. I'll try to be back at some other point.
Always a pleasure to have you, Sandy. Go back to zapping asteroids.
Pew, 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 pew.
Okay, so Kimberly, you proposed 3 stories, and I want to talk about detecting biosignatures in exoplanet atmospheres because that's about the thing that I care the most about.
Alrighty. So we've talked. The news and the media have talked a lot in the past few years. Now that we're finding more and more exoplanets, we're naturally finding more and more exoplanets that are in that exact sweet spot around their stars in order to host liquid water. Mars is one of those planets that is in the habitable zone, even though it's a bit too cold. But Mars brings up an interesting example, is that it is in the habitable zone, but except for a few very specific cases, doesn't have flowing water on the surface. And so there's got to be this more expansive definition of what a habitable zone is, what makes a planet habitable, and the biggest answer to that is not just where it lies in relation to its star, but what kind of atmosphere it has. And we're getting to the point in our technology where we can actually start to measure what the composition of the atmospheres of some exoplanets are. Now, right now we're very limited in that. We can only look at so-called hot Jupiters, which are very close to their star. They're very hot and very easy to see. But with James Webb Space Telescope, one of their goals is to actually look at the atmospheres of planets, which opens up an even bigger can of worms of if there's life on some of these habitable zone planets with great atmospheres, would we actually be able to detect that? Is there some sort of trace in the atmosphere from any life that exists on the surface? So that's the question. The answer to that is a lot more complicated than you'd initially think, because a lot of the great tracers for life that we see here on Earth, for instance, chlorophyll from plants, you can't really see very well through our atmosphere from space, even though it has a very nice distinct feature that we like to call the red edge. It's a very sharp drop in the infrared. And we say, ah, great, that's a great signature, but you can't see it through the atmosphere. And so you come up with all these other, what kind of chemicals can you see that are produced by life? And the easiest one to see, actually, is molecular oxygen and its product, ozone. And those are the easiest things to see. But you have the problem of molecular oxygen and ozone can also be created without the presence of life, just through natural chemical reactions that happen in the atmosphere. And
in large enough quantities, and they can last for long periods. Oh, there goes that idea.
But there is a ray of sunshine. Sorry, pun. There's
hope.
There is hope. The issue of whether or not these detectable amounts of oxygen could build up in an atmosphere is really dependent on what kind of star the planet is around, because it depends on how much extreme ultraviolet light and not so extreme ultraviolet light that your star is producing. So, long story short of it is that the perfect types of stars to look for biotically formed oxygen in the atmosphere is actually the sun, G-type stars, and actually F-type stars, which are slightly hotter, just because the extreme ultraviolet light is not as strong compared to the not as extreme ultraviolet lights.
So if around the G-type stars, we can then potentially detect, by studying their atmospheres, get a sense of whether or not there's life there, and be able to tell the difference between whether it's natural forming causes of creating, modifying the atmosphere, or whether it's actually being caused by life.
Exactly. So it gives us more confidence that if we ever did detect large quantities of molecular oxygen or ozone in the atmosphere of a planet around a G-type star or an F-type star, we'd have a pretty good confidence that it wasn't caused by any natural process.
So what terrestrial planet-finding telescope would one use to be able to actually study this?
I would highly recommend James Webb Space Telescope.
Is James Webb going to have the capabilities to do this?
It will. It will have. It'll be very strong in the visible and the near infrared, and there are certainly plenty of signatures of oxygen and ozone that happen there. It'll have, I think, two different spectrographs that I know of, possibly one that I don't know too much about. But it will be ideally placed to find these types of planets, and not just the ones that are super close to their stars, like hot Jupiters or habitable zone planets around M dwarfs, for instance, but to actually move out towards more Earth-like distances.
And as we talked to Sarah Seeger from MIT, with the coronagraph, you can really get a much better view of the planets orbiting other stars.
That's true. You want to remove as much of that contaminating starlight as possible, so you know, I'm only looking at my planet.
So just philosophically then, do you think the aliens know that we're here?
I think if the aliens are looking, it'd be hard not to know that we're here. We send out a lot of signals. We're very loud.
But in terms of just our life, like we're loud in terms of the molecular oxygen we put into the atmosphere. I mean, with our radio signals,
Sure.
maybe not, but just purely just the
Molecularly.
biosignatures of molecularly, we're very loud, and the aliens would know that we're here.
Well, yeah, go for it.
Oh, well, I was going to say, it plays into the same argument, is that we are around a G-type star. It is very unlikely that there is that much molecular oxygen or ozone produced abiotically on the Earth. In fact, the largest oxidation event that happened in Earth's history was caused by this big blooming of bacteria on the Earth. It was exactly caused by an explosion of life on the Earth. And from newer studies, we know that this doesn't happen. These large outbursts of oxygen don't happen when you don't have life.
Yeah.
So I think, it's totally possible that if some distant alien civilization were trying to take a spectrum of the Earth, they could say, wow, that's something that doesn't happen naturally. There must be something else going on there.
Yep. Send in the berserkers. Okay, let's move on. Pamela, let's talk about some maps of Ceres.
So Ceres is continuing not to want to reveal her secrets.
What is the light on Ceres?
We don't know.
No. Come on. We sent a spacecraft. It's taken a bunch of pictures. The pictures are higher resolution. It's right there.
I understand. So the problem that we're having as we move into fall in planetary science is we've got these two spacecraft, Dawn going to Ceres, went to Ceres, still at Ceres, New Horizons, well past Pluto. And as they visited these two former planets, they found geologic phenomena that makes no sense. And everyone's heard about Pluto. We've talked that one to death, but Ceres gets no love. And currently it also gets a whole lot of mystery coming its way. So the maps that NASA released this week are new surface topography maps that have been false colored to make it really easy to tell differences in altitude of different objects. And my favorite of these so far is one that shows the 4-mile-high mountain of no explanation. So we joked at the top of the show about monoliths being in the movie The Martian. No, they're actually in the actual images coming from Ceres, where there is this large, flat-topped, if it was in the American Southwest, I'd call it a mesa, except there is no known geologic way to form a mountain like this on a dwarf planet like Ceres. And so Morgan's pulled up the surface maps here that you can see. And the other confusing thing is we still have these shiny points down in the bottom of one of the larger craters. And we're still at the stage of we don't know if this is ice, we don't know if this is something that was deposited or revealed when the crater was formed, we don't know if these are salts, we just don't know. And at a certain point, one of the great frustrations of orbiting spacecraft is you don't always have all the instrumentation you want. And in this case, the instrumentation we have just keeps giving us new mysteries. These also include getting some gamma ray detections due to interactions with, we believe, solar radiation. And every time NASA releases a little bit more data on this little tiny world, we just find ourselves scratching our head a little bit more, and soon the whole planetary community is going to be bald.
It almost feels like with New Horizons, we got a bunch of surprises, but they were like, yeah, look at that. There's mountains of ice. There's glaciers of frozen methane and ammonia, but it sort of made sense. As weird as
Ceres, it
was.
makes no sense.
Ceres, they just still like they forgot to send the salt ice analyzer to figure out which one it is, right? And and the
Right.
monolith.
Yeah,
Extractor.
that one's just sort of like how, and there's only one. The fact that there's only one somehow makes it even more annoying. But the other thing that came out with these maps is the folks working with the Dawn mission have done a really good job in producing their maps and working with the International Astronomical Union to get approved names for the different objects. Ceres goes with the goddess of Surreal, kind of makes sense. And so in naming this world, they've worked to have a lot of the gods, deities, and cultural myths surrounding agriculture have been tied into the naming of these different features. So this little dead world of rocks and either ice or salt is named after all of the things you might need to celebrate, well, growing stuff. So we have a good dose of irony to go with it.
All right. Last but not least, Brian Koberlein. Let's talk about mysterious gravitational waves.
Okay. Well, gravitational waves are kind of the last mystery of general relativity that haven't been directly observed. And basically, within general relativity, because it's not occurring instantaneously, if you take masses and you move them, like black holes orbiting each other or something like that, they create these gravitational waves, and those gravitational waves radiate out from the binary black hole or whatever. And we have indirect evidence of this, and that's through what are known as millisecond pulsars. And these are pulsars that are spinning really fast, and they do, fraction of a second pulses of high energy radio waves. And we can measure the positions of these things very precisely. So if you have a pulsar that's orbiting with another star, we can measure the orbit of that pulsar extremely precisely, and we can watch over time, and we see that its orbit degrades. It spirals inward toward the other star over time. And the way in which these spiral inward exactly match general relativity and the emission of gravitational waves. Well, this was done, I think, back in the 70s, the first time the work was done. And so we've continued to do this, and we've gotten more and more precise in our measurements. And what's cool about this latest work that's been done is we're getting precise enough that not only can we see the spiraling, but we could see effects of those. So any other thing coming in on it would cause them to kind of oscillate a little bit. So the basic idea is this. If you have all these things like black holes and pulsars and neutron stars and everything creating these gravitational waves, it should be kind of like a whole bunch of different things rippling in a pool. So you should have these gravitational waves just kind of moving through space. Not necessarily very big, but big enough to measure. And so if these two pulsars are, a pulsar is orbiting another star, we should be able to see that oscillation because of all those ripples. So they did this as a 12-year study. And what they found was nothing. Bupkis.
Uh-oh. Was Einstein wrong?
Well, no, it's interesting because their sensitivity is enough that we would have expected to find them. And what they did is they measured, theirs put a constraint of that's much lower on what these gravitational waves could be. Now, there's a lot of explanations that could possibly account for this. And one of them is that gravitational waves may be weaker than we thought. general relativity might be wrong. And even though we have direct evidence of gravitational waves, maybe they're weaker. Maybe they dissipate faster than we think. That's one possible thing. The other thing could be that the way the gravitational waves form, their shapes could be different than we expect. And so what they were looking for, the type of kind of frequencies of the oscillations that they're looking for, may be different. It could be that, you know, one of the things that would be a big source would be binary black holes that are merging. It could be that binary black holes don't take a long time to spiral slowly inward. There may be some mechanism beyond general relativity that causes them to spiral in quickly, or it may be that their accretion disks interact in a way so that they spiral in quickly. So they'd have a much quicker in-spiraling, and they would produce then less gravitational waves. So there's all these possible solutions, but what's interesting is we now have kind of an observational limit on what these gravitational waves might be. And that now throws it back to LIGO and those folks. It's going to be harder for them to detect.
Oh no!
So just as they were right at the edge of, we can detect this. Oh wait, no, it's harder.
How much harder?
I don't know what the exact factor is, but it's actually, this was a really good observational limit. This should have found evidence of gravitational waves, and it didn't, and that was surprising.
Well, and there's a few people who are still holding out that maybe we just haven't characterized the noise in the data appropriately.
Right, right.
And I have to admit that's kind of where my gut is. Now, guts don't speak science.
Right.
But the fact that the folks working on studying the gravitational constant, which is a different set of experiments in Seattle, can measure the change in mass of the nearby mountains every time it rains. Gravity is one of those things that everything going by can affect things at the scale that these gravitational waves are expected to be at. So simply not characterizing our planet well enough may be the underlying reason we haven't detected these yet. Now what's interesting is they've already given the Nobel Prize for detecting gravitational waves, and that went to Joseph Taylor and Russell Hulse in 1993 for their work on binary pulsars. So the Nobel Prize is out there, so folks are now fighting for a different form of glory.
Right.
But it's a fairly strange situation because, as you say, right, on the one hand, the gravitational waves were detected with these pulsars that, you know, very good evidence that it is causing it to sort of lose its angular momentum, and the pulsars are getting closer and closer together, and yet, and completely within the predictions by Einstein, and yet with this other set of observations they're not able to do it. So, I mean, you know, is there a place where they have to stay, okay, maybe Einstein was wrong, that maybe it wasn't gravitational waves that we're seeing, that it's some other effect that was causing the pulsars to degrade in their orbit?
I think that would be really surprising, because the Hulse and Taylor observations and the similar ones match general relativity really well. And the thing is, it's not just that the simple rate of the in-spiraling matches, but we have binary pulsars in which you have a different shape of orbit. So one may, instead of just being circular orbits, they may be coming in and going out, and those rates, and not only those, the precessions of those orbits match general relativity. So we have multiple points of observation that says general relativity works. That's what makes this new result so surprising.
The place where we're really getting expletived is the LISA spacecraft would have had huge technological hurdles in getting constructed, but once on orbit would have had significantly greater sensitivity than we have here on the surface. And Gravity Probe B and other missions have mapped out the gravity around the Earth really well so that we'd have a solid understanding of the background that they're dealing with. But because the pilot study here on the surface of the planet has failed to turn anything up, it's really hard to get buy-in for a mission when your test on the planet failed spectacularly. Right. I remember back in 1993, someone coming back from a summer RAU, like, yeah, I worked at LIGO all summer. We're a year or two away from finding these gravitate. No.
We're 20 years away from fusion, so.
Yeah, 20 years away
Yeah.
from fusion. So we might have to go back to the drawing board and increase the sensitivity by another factor of 10.
Which means orbit.
Yeah.
That would be so sad, because they just brought it back online, and somebody had mentioned some kind of rumor somewhere on the internet about a detection from LIGO, but we'll wait for that to be more substantiated. So we've got about 5 minutes left. I'm going to throw in a couple of questions here that we've got from some people. So here's one for you, Kimberly.
Yeah.
Comes from longtime fan, Andrew Planet. Well-named Andrew Planet. So does a habitable zone that entail having... Oh, we lost your... Where'd it go? Man, I just lost his...
Is it the
no.
Mars one or a different one by him?
No, we want to talk about water, but I just...
Okay,
it just
scrolling.
Hold on. Man.
Oh, got it. Thanks, Kimberly. Does a habitable zone then entail more than having liquid water on a world? If life occurring on it depends on the star, or is that just limited to oxygen-dependent life forms?
That's a great question. So a habitable zone planet does not necessarily imply that there is going to be liquid water on the surface at all. You have to either form with liquid water there or somehow have water deposited onto the surface. A habitable zone, in the traditional definition, simply just means that if there is liquid water, if there is water on the surface on the planet, then it will be in liquid form. But if you have an improper atmosphere, like with Venus's atmosphere that is way too thick, it changes the surface temperature, and so your liquid water might not actually be able to sustain itself for a long enough period of time. In the opposite case, there's Mars, whose atmosphere is just too thin, and so any water that is on that planet is in ice form, and that's not really conducive towards sustaining life. There's also the additional complication of if you have an improper star type, you may be receiving too much really harmful radiation, such as X-rays or ultraviolet lights. Our atmosphere does a great job at filtering most of that out and protecting us. But if we were around a different type of star, our own magnetosphere and ionosphere may not do such a great job. So habitable zone doesn't automatically imply hospitable for life.
And hopefully in the future we'll have better analysis of these planets and say, here's one that we know actually has liquid water. Because as you say, Mars sucks, Venus sucks, but they're both in the habitable zone along with Earth. And so, aliens would look at them and say there could be life on all three planets. 3 planets in the habitable zone, but
and worse than that, Europa, not in the habitable zone, not a planet, has liquid water.
Yes, it does. And so you have that additional, maybe there's some kind of heating from another source, like Europa has from the tidal heating of Jupiter. So it's a very complicated question, but the good news is that based on what we know of our own solar system is that water is everywhere. So it does increase the chances that it could be on whatever exoplanet we find, in whatever form it takes.
All right, I'm going to take one more question here. This one comes from Chris Macca. Is there a way to balance planetary protection protocols and searching for life on other planets? Morgan, what do you think? Can it be balanced if you find these really fragile, precious, beautiful European space whales who are really sensitive to Earth bacteria? Can we ever visit and swim with them?
Yeah, this is sort of the ultimate trouble with searching for life in the solar system is that this question of protection goes both ways. If we send a spacecraft to another world, it will have Earth bacteria on it. We've yet to send anything anywhere at any time that doesn't have something somewhere riding along inside. And so there's always that chance of contamination. And if we discover life on another world that looks a lot like our own, we're never going to be able to shake the question of whether or not we brought that along with us or whether we found it there. And then, of course, if we do find something that we think might be some sort of alien life, in order to truly understand it, we're going to need to try to bring it back to Earth. And, given some of the troubles we've had with sample return missions in the past, it's unlikely that we would be permitted to bring such a thing back alive, as you have suggested. And, it would be, sort of a shame, I think, if the first thing we had to do when discovering alien life is kill it. But that may ultimately be, a message from our planet and the necessity of that exploration requires.
Or only observe it from afar, right? Like if we do discover somehow that there is life, like for example, if the Europa mission detects the evidence of biological life in the on the surface of Europa, then what do, right? You don't want to go down there and start mucking around with it and infect the whole world with Earth bacteria.
Remote sensing. Remote sensing is the key to everything. We need ice-penetrating radar and.
Yeah, well, they're sending it. But again,
the trouble
let's
is,
say it's there, right, Pamela? Like if it's there and you know it's there and you can wave to it, but you can never visit it because you'll kill it all.
All I can say is smallpox blankets.
Yeah.
And this is where remote sensing is really the only way not to destroy things we don't understand.
Yeah, and we're not there yet. We don't even know that there's life under in the lakes under the ice in Antarctica without drilling down and bringing it up and putting it under a microscope. And until we can do that with the relatively shallow and relatively hospitable locations here on Earth, we're in no position to try and understand, from orbit or from 20 feet away, what alien life might look like. And I think that's sort of the fundamental problem that nobody talks about when discussing the search for life, is that we're not equipped to understand it, even if we find signs that perhaps it might be there. And it's far more likely, at least right now, that we would discover our own dirt than we would discover anything from another world.
Yeah. We would need to find something really alien, like a DNA that is mirrored to our was it left-handed versus right-handed? Anyway, and all the people talk about terraforming things, like this guy is what if we destroy an entire habitat to make it more?
We have a terrible legacy of having done that.
Yeah, exactly.
Going forward.
And yet here we are, Venus forming Earth.
Yeah, but that's also one solution to the Fermi paradox.
Snowden, actually, of all the people to come out with it, came out with an awesome idea for solving the Fermi paradox, and the idea was, what if all advanced life forms have figured out that you really have to encrypt stuff if you want to protect what you care about, and just like currently we use as a form of encryption ionospheric noise in some radio signals, what if they are encoding their signals using cosmic microwave background? Anyways, that was random, but it was one of those things that was like, why have we not thought of this before, and let's encrypt all the things this way.
Yeah, I think people had thought about that before.
I had.
I hadn't either, cool. But a few. This was a Twitter conversation we were having, and a bunch of people were like, "Yeah, no, that's." People thought that one through. But why don't we wrap things up? Let's give people a chance to shamelessly self-promote themselves. And Brian Coberline, you're already ahead of the game here. I see you have a new affiliation with some kind of website.
Yeah, you can find me on Twitter at Brian Coberline, and you can find me on my website at briancoberline.com, and now you can find me on Forbes.com, where I'm a contributor of occasional posts.
Are you writing new posts for them, or repurposing stuff you're doing on your other web?
Brand new posts. Wow. So that you'll see them on Forbes first.
Well, they're lucky to have you.
Well, thank you.
And let's say that a person wanted to contribute financially to your future. How would you do that?
You can go to patreon.com/Brian Coberline.
Awesome. What's an example of a reward someone can get by contributing to your Patreon campaign?
Well, we're less than $100 away from videos now. So if you push me over the edge, I got to start making videos.
Awesome. Welcome to my world. Kimberly, where do people find out more?
You can go to my Twitter handle at AstroKimCartier. I am not an astronaut, though I've been told that that is a common prefix for Twitter handles for astronauts. You can go to my Twitter handle, and if you go to my profile there, it has also a link to my personal website where you can find out more about my professional research as well as a bunch of writing and blogs that I do there as well.
Fantastic, and thank you very much for joining us this week, for
Oh, it's a
bringing the
pleasure.
exoplanets, and let us know if you want to come in the future. That'd be great.
Anytime you ask.
Morgan, where can we find out more?
Well, you can also follow me on Twitter at Morgan Renberg. I'm also not an astronaut. Or you can check out some of my most recent work over at morganrenberg.com.
Dr. Pamela Gay.
You can find me tweeting as @StarStrider, and I'm also CosmoQuestX on Twitter. I personally occupy starstrider.com and professionally cosmoquest.com, .org, cosmoquest.org. And I also have to give out a random shout out of thanks. Thomas Traniker sent the SIUE staff an entire box of candy where the first thing I did was I stole a container of green gummy frogs because they were adorable, and I ruthlessly ate all of them very quickly and deliciously. And they were very, very cute, as you can tell from the packaging. So, yeah, Scandinavian candy is kind of awesome. So thank you so much, Thomas. You really made all of our days, and we now have a sugar-high staff. So thank you.
Perfect. Awesome. Of course, Fraser Cain, you can, wherever you're watching this, just subscribe on the YouTube channel, and you'll get more of this and also the Parsec Award-winning Guide to Space videos that we do. We're going to be shooting a bunch more next week, so we've got some good ones coming up. Like we talk about Boltzmann brains shortly, which is pretty fun. And I also want to remind everybody, I mentioned at the top of the show, but take some time and join the Weekly Space Hangout crew community on Google+. They really are the producers of the show. They're the ones now that sort of figure out a lot of the stories that we're going to be tackling. They arrange our special guests, including some really amazing special guests that we've already had, and some even more amazing special guests who are coming up, which I can't talk about until it all happens. But yeah, I'm really excited about the guests that we've got coming up. So if you want to, Google+ community, join them. Weekly
Twitter,
Space Hangout
WSH Crew.
WSH Crew, and they have now, I think it's wsh-crew.net. Anyway, they have a website as well, so, or maybe it's all one word. I apologize to the WSH Crew. Anyway, join them. They're awesome. They really make the show happen, so thank you. Couldn't do it without them. All right, well, hey, thanks everybody for joining us for the Weekly Space Hangout, and we will see everybody next week.
Bye-bye.